I've opened my EM. One thing to make sure you do is you open the workstation version, not the client, because you already you installed the workstation version. So I've already opened it, but the way you do that it's similar. You go SAS Enterprise, minor workstation. Make sure you open that workstation. So this is the let me open a sample project for you, just to get a taste of the interface. Okay, let's see. Okay, so that's the main interface. All right, let me stand here. So as any other software, you have the file, the menu buttons and drop-down menus under each, and these always stay the same. And you have a bunch of shortcut toolbar of shortcuts. That is somewhat routine tasks that you would do, but actually you rarely do it. I don't know why they are there. And below that you have a this is the project view or project panel. So all the project files or project objects are here. Three main things. You have the data sources. You have diagrams, or that includes the basic work area of your process models for data mining projects. And also you have other model packages, which are imported tools. For now, we're using the other two mostly. Below that, you have a property panel, properties, characteristics of different objects. And because there are different kinds of objects here, there are data sources, and there are diagrams, and within the diagram you have processes. And two basic elements of a process is the nodes and the sequence. So there are various objects here. Every kind of object has its own property, and every model has different sets of properties. So this area is going to change, conditional on what kind of object you're working on. So it's kind of like a contextual menu here. But you'll notice now it's very short. It doesn't have many options to change. But later on you will see more options. This part is more of a help tool. It provides miscellaneous information about some. If you click that, it'll explain what this row says, and provides pointers to additional resources. Okay, so I'll open this diagram. A typical diagram is a vast white area. It's like a canvas. You put stuff on it and make a process. The two basic elements here, you have nodes. Is the boxes of things, but they are actually of different type of nodes. You have data node, you have some exploratory tools, and some modeling tools, evaluation tools, and other data related tools. We'll get into the details. You'll see that here all of the nodes have a green tick mark. That means this node has been run, and you can extract results from these nodes if you want. If you make any change to these nodes, then that green tick circle will go away, indicating that you need to run again before you can trust the results. And there are buttons, there are menus right above the this is the diagram panel, right? Like the canvas, and each of these buttons will bring up more buttons. These typically don't change. There are, there are many options here, but mostly what these does is to make it easier for you to create exactly the type of node you want. All these tools, majority of these tools are to create a specific type of node. So under the model tab, you have a dozen of different models to create. Now, every button create a type of model. Some of them may be similar to each other, but some of the others are different. And it even have some text mining applications here, time series, more advanced analysis. So a basic explanation about the interface. And I'm going to start to mess up with the nodes. When you click a node, the contextual menu for the properties changes. It changes very dramatically sometimes. It does have the basic sections similarly. It has a general section, it has a train, because all of these are kind of model-based nodes. So they have the train section, but under the train section, what kind of properties you can modify with that model depends on what the model is. Okay, a little bit about working with the processes. After you drag and link, you can move things around. You can link two nodes by dragging from one end to the other end, and then when you move the other one, it will stay. I know that some of your laptops are very high definitional, and the nodes look like these. So if you face this situation, then simply enlarge it. Don't make it too hard on yourself. But if your menu items are too small, like you have a high definitional, screen, video card, and your daily resolution will show very small menu items, then you would have to change the resolution. That is what I found out to be the most effective way. If you try to mess up with the font size, it gets funny. Sometimes the line breaks without making it very comfortable to look. So that's what I find out to be the best way. But talk to me if you have that problem. So you can zoom out, you can zoom in, and you can also arrange it in a way that's neat. So there are some options here. You can use the auto arrange feature to put them on the horizontal line, sort of make it prettier. You can change that. It won't be exactly what you want, just because there are many things going on here. But based on that, you can tweak slightly to make the way you want, right? So I find that to be, and you can also make it vertical, like from top to down. It's like a waterfall, All right, so it's just your style. Choose whatever you like. So that's a quick walkthrough of the interface. And we're going to do specific projects. Any questions so far? Right. Close the project like this. Be careful not to, even in a rush, don't click this, because it just goes away. It disappears. It just completely goes away. But it will remind you. But then in a rush, you'll say yes. You're thinking that you're closing it, but it's deleting, it's shredding, and it's gone. I had a team is approaching the end of the project, and one of the team member had the project lost, like that. That's painful. So be careful. Saving. Okay. All right. So good. We're good. So I'm gonna do this, right? A lot of the first few chapters here are informational. And, they're informative. They explain what I just demonstrated. You can look at them, in detail later. The beginning of the project here, the sample project, starts from chapter 3. So I'm just go right into chapter 3, page 9. So follow me and make sure you have a partner. Bronwyn, do you have your SAS ready?
I'm going to bring my laptop today.
Come sit over here.
Yeah, if that works. Shu, do you have your software?
Yeah, should we get a version or no? I don't know how to. I thought you had a different one.
You're gonna have to drag a chair.
Bronwyn, I think it will be probably easier if there's not much space here. If you work with Shu, it might be better. Make sure you have a partner. How do I? You have that. Not yet. Okay. So that's fine. We'll go from the beginning here. So let's make it work. So Jose and Sherry, hope to
This one.
So I think you can sit by the room. We'll make some space here. Jerry doesn't have the software ready, so we need a chair. All right. Make sure you download the SAS data file. It's a donor raw, right? It's not donor raw. From this week's folder. Right. So prepare the data set and I'll wait for you for a couple minutes. Make sure you have them ready. We'll start right away. The other, the data set from this week's folder, week 2.
It's already in the. Professor, you want to have it loaded in the directory folder, so we can just import it?
Yes, if you already done the library part.
Yeah.
Good. Alejandro, need more time with the data set? Good? Everybody? Good? Okay.
We don't have to go through enterprise again, right? Because it's already a SAS table.
You mean enterprise guide?
Yes.
No. Yeah, it's already SAS table, so we'll work with SAS EM. Okay, we're gonna start. So we're gonna start from basically from page 9. But I'm gonna be pretty fast. I'm not gonna explain exactly every piece of information, but I'll highlight the important ones. But anytime if you have questions, stop me, let me know. So open your SAS EM. We'll open the first project here. So name for here it's a donation, so I'm gonna use a slightly shorter name. I don't like long names. I use charitable or charity. as a project name, I'll put it in an EM folder that I typically keep everything related to EM in the directory. So it's like that. And you'll see some summary information about the project, and then the project is created. Very simple. Now the next step typically is to load in the data set. But for any new project, you will need to create something that's called library, which is a shortcut to a directory. And library is not a sort of an explicit entity here. So you will have to go to File and New and create a library. So you can use any name. It's as long as it's 7 characters or shorter. And point the path to the folder that you keep the EM resources. And it's a summary page. And just click finish. Any questions? No? Everything's good? Great. So that's preparation steps. Now you can create the data source. You can either right click or use the same new file new. Same result. So you want SAS table as the only option. Try to find it. You'll see a list of it's a kind of a different directory structure, but you'll find the library that you just created and look for the data set we're going to use. It's donor raw data. Yeah. And some miscellaneous information. You'll notice that there are close to 20,000 observations, which means rows, number of rows. So for the Excel, from the Excel standpoint, it's a large table. From SAS standpoint, it's not large at all. It's a piece of cake for SAS, but and there are 50 columns, 50 variables. Here, let's see. Are we doing something here? I don't think so. Oh yeah. Well, let's see. No, we're not doing anything here. This is to teach SAS how to be smarter in guessing what you want. But for now, we can skip that. I don't think it's in the steps as well. Yeah. And the next step, this is pretty important. So this is to specify some meta information about the columns here for the sake of modeling and data mining purposes. So this is getting a little deeper into the EM context for better modeling and using these data sources. As you would expect, the gray areas are a list of variables. There are 50 of them, right? And immediately following that, so this is not the table itself, right? It's a metadata view of the columns. A critical piece of information is the role of the column. Typically, for most of the models that we will use, all of the supervised learning algorithms, including decision trees, regression, neural networks, they are only one target variable, which is one of the role here. If you look at the drop-down menu, there is a list of different roles here. Two kinds of roles are necessary for most of the models we learn. There are exceptions later on for other kinds of models. For now, you'll be used to this convention. We'll have one and only one target. So one of these variables has to be target, and only one variable can be target. Most of the other variables will be input. So that's why you see most of them input here. But toward the end, you see two target, right? So one task that we have to do is to decide which target to retain and what to do with the other one. So here, you are going to retain the target B. So, without changing anything about target B, but for target D, we're going to reject the variable. And the reason SAS put target as the role for these two variables, can you guess? Yeah, the name, because the name has target in it. So SAS guessed. It's pretty smart, but you can see the limit. We typically wanted only one target, not two. But anyway, so give you a little bit background here. This is a data set about donation campaigns. So imagine a marketing company is sort of soliciting donation from a pool of potential targets, right? So they have their phone number or mailing address, other demographic information, neighborhood information, maybe credit scores, maybe profession, marital status, everything that's easier to collect or buy, and then they can sort of make a model of predicting who are those that are more likely to donate than the others. So then they can target differently. And this data set records the results from previous campaigns as well. So this is one of the campaign here, and two targets here record two pieces of the critical information about the outcome. Target B is a binary variable. This is the term we use. Binary is there are only two different values with this numeric variable. It's 1 or 0, yes or no, meaning it's a dummy kind of variable. It records whether or not this person, this potential customer, donated or did not donate during the last campaign. So it kind of tells the machine some information about the outcome. What happened to this customer, given his or her other information like age, credit score and things like that, income, so that machines can infer by trying to find patterns, links between those other variables and with the target. So you can kind of imagine an algorithm that links those other information with this critical outcome information to the point that maybe, given enough accuracy, then the algorithm can predict more accurately about a future customer given these information, so that business can make decisions more informed rather than guessing or hoping everything works, right? The companies can, based on the recommendation from the model results, the company can avoid targeting a segment of the customers because the predicted response is very low. So a little piece of information. We're going to use that binary variable as a target, but the other variable is the amount of donation that was made during that campaign, if that person donated. So can you imagine the two variables? Let's see. So the two columns, one is a binary indicating whether the customer donated or not. The other records the amount of donation of that person. Do you see any problem? Or can you think of any? So what will be the values of these, the two columns?
So if it's a yes, then we'll see a value. If it's a no, there'll be no, yeah.
It'll be empty.
Blank,
Yeah, because we don't know. And then this piece of information is unavailable. Yeah. So this is relevant to the missing value case, and we're going to talk about later. Right. Right. Keep that in mind. And all the information I said is in the appendix portion about this specific data set. You can find it on page 60, something like that, or 50, 58. Okay, so we did that. For the rest of the variables, we'll keep them as is. Right. Okay, this is a long list of variables. We'll take a look at what the information we have. We have homeowner, whether or not this person owns a home or renting or other status, age, gender, and lifetime gift amount. Like cumulatively, how many in total this person has given. And SES, even socioeconomic status, different tiers, different categories. Yeah, so quite a few variables here. So we can go to the next step. Let's see. Do you wish to create a sample? We're going to use the entire sample here, so we'll say, well, default is no. We'll go to the next step. This is still fine. Make sure, but the default is raw. Choose the raw, because we will make partitions from this data set to be training and validation. So using the raw will be the most inclusive one. You have a summary list of types of variables here. So here, a little bit of other background. What is interval variable to you, from your understanding? It is a number, yes. There may be different kind of numerical variables, interval being one of them. What do you mean a range? There's a range. But what are the other kinds that you can think of? It's also a numeric. Decimal. Let's see. Does nominal make sense to you? What is nominal?
So a name could be something with like letters.
Yeah, something like that. So nominal, sometimes referred to as categorical. It has a limited number of unique values in it. Like for example, gender. Let's see, gender has only 2, maximum 3 categories we typically use, right? And something other, education background. Primary, elementary, middle, high, 6 or 7 levels. For these, we call them nominal or categorical sometimes. But sometimes they are recorded as numbers as well. But indeed, they are referring to some categories, not, the numbers exactly, they don't make exact meaning, right? If we code female as 1, male as 0, the numbers it's not meaningful per se without the meaning behind it. So that's nominal. But interval, or that those values are meaningful values, and the range can be infinite. It's continuous, and it's typically decimal as well. So the decimal values can make sense. 0.5 means half of 1. So in that case, that's continuous. We sometimes call it continuous variable, interval variable, or simply a numeric variable to refer to this kind of variable by default. So we have, in a special case of a nominal or categorical variable is a dummy variable. Dummy variable is a binary variable. It's same meaning. A variable that has only 2 possible values, right? High or low, large or small.
Would temperature be interval? Like the temperature?
Temperature. Very interesting. Very interesting. We typically treat it as interval. Yeah. Yeah. Although it's not as exactly the same as age. I mean, in terms of the intervals between the values, 80 degree and 81 degree, the difference is 1 degree. But this 1 degree, is this 1 degree of difference the same as 60 to 61? May not be the same, because it comes down to feeling. But age of 1 is always true. Age difference of 1 is 1 year, and the time is defined. But temperature is not. It's a little fuzzy there. But for the analysis purposes, we treat them the same. Yeah. Great. So I think I skipped some step about the decisions somehow. Let's see. So I think somewhere in the middle, I click next, but probably shouldn't have. But we can get back to the steps there. So we want to customize the decisions and the probabilities here, and the reason is I'll talk about later. Come on, take some time. Maybe in the back. Yep. No class targets. That's interesting. So sometimes you'll face a problem like that, but try to debug. It has to be something about a target. So target B should be binary. Here I left it as interval. I shouldn't have. It should be binary. It makes a material difference to the models. For models of classifications, like try to predict a donor or not. That's a classification problem. It requires the target to be categorical, so it cannot be interval. It's actually binary here, so we'll do that, and hopefully we can do the decisions here. Right. So we'll build, according to the tutorial, we'll build some parameters about the decision criterias. So think about the context again. It's making donations, right? And the purpose of the model is for the machine trying to learn what kinds of characteristics about these customers help predict whether or not this person is going to be a donor or not, right? That leverages the relation, the correlations, the covariances, and the structure of the covariances between those input variables and the target, right? And then companies decide to elect one decision based on one outcome. If they predict this customer to be likely a donor, then they should make the decision, or likely to be sending out a solicitation, or make a phone call, or maybe send a mail, postal card, to ask for donation, and that is that costs money. In the ideal world, you can send it to everybody, but that's not realistic. You have to think about the cost. For somebody who you don't predict as a high likely donor, then you'd rather skip that person, but and focus on the segment that has higher likelihood of donation. So that is the case here. So let's follow the tutorial. We'll build the criteria for the decision model. One thing to change here is the prior probabilities. And the reason is one. In the data set, a summary statistic of that target, that's target B, is that 25% of the sample has a value of 1. So that means 25% of the sample made a donation during the last campaign. 75% of the sample didn't, has a value of 0, right? Now, if that's the case in real life, that would be fantastic. But realistically, it's not typical. So do you know typically what is the percentage of people donating money in any context?
Only less than 25.
That's a smart guess. Yes, it has to be. I kind of hinted. But what is the level that you can guess or know of? 10%. 10%. From Dennis?
Yeah.
It's a good guess. But not quite yet. Another try?
3%?
3%. Quite close.
Okay.
Yeah. 4 to 5. 3, 4, 5, something like that. So very, but that's reality. And you kind of, it's rational. Right, it makes sense, right? So that's a problem that the data analyst has to face. So let's see, if you try to collect a data set, you have a kind of a large sample size, 20,000 like this one. If only 5% of the sample make donations, how many observations do you have about donors? Let me do the math. 20,000 times 3%, 600. Yeah. So you only have 600 cases of donors, where you have the majority of them non-donors. So this data set is highly skewed toward non-donors, and tend to not have enough observation to learn for the machine about donors. So that is a problem. If you train the algorithm using that kind of a data set, it's going to give you a large, it doesn't have enough to learn about, about the donors. So in these problems, you face kind of a, undersample problem of the donor. But this is not only in donation case, it's only in other business or other non-business situations. Can you think of one? Like, a phenomenon that is worth predicting, but the chance that one of the values, let's think about binary situation for now, right? Because there are only two outcomes possible for one phenomenon. One side has very low representation, it's a low percentage, the other is the majority of cases. Can you think of one case? Elections, in which sense, like the winner?
Yeah, there's going to be, we're usually there's going to be either or.
Okay, so you mean a bi-party election case? Can you, so in this context, can you think of one metric that you're trying to predict?
How many votes they receive?
How many votes each side receives. It is a binary choice for any ballet, right? But it is a little bit. It's not the kind of a predictive problem we try to say. Think from the presidential candidate point of view. Let's see, for a geographic region, the party is trying to estimate the number of votes versus the other side, or percentage of votes that the candidate can secure. It's not quite yet the kind of problem. Okay, let me give you an example. Predicting serious disease like cancer. It's a yes or no. The majority of the cases, it's no. Majority of the cases, and hopefully, right? But in some cases, it's yes. If you construct a data set, then it's only going to be 1% or maybe 3%, a low percentage of cancer cases versus healthy cases, positive versus negative, and it's going to lead to the same problem. Another technology-related case is cybersecurity. Cyber attacks. If you observe the sort of the visitors of the website, then it's going to be very low percentage that they are hackers. But for the machine, the objective of the tech team is trying to predict which visitor is the hacker, right? So they face a similar problem. A very low representation of the positive case that they try to predict. That's the kind of problem here. So the technique to deal with that is to do selective sampling. Selective undersampling and oversampling of the different cases. For cases like this, you want to oversample the positive cases and undersample the negative cases so that there's a good mix of and a good representation of both cases so that the machine can learn and increase the accuracy of the model. And that's why the sample has higher percentage of donors, even though in reality it's not. But for the model to properly construct the final solution, we have to tell it that in general, what is the percentage that we expect the positive case to be? Not like how it's represented in the sample, but in reality. That's why we need to tell it the prior probability of these two situations in reality. So here's what we do. We need to change it. Do you want to enter? So adjusted prior probabilities. We'll put 0.5% here and 95% on the other side. Yeah, and not hit OK quite yet. We'll have to customize the decision as well. Okay, now, so here is the decisions that the businesses can choose to do. And if you're the business, let's say one objective can be that you want to predict whether or not a person is donor or non-donor to the highest level of accuracy as possible, right? You want to increase the accuracy performance of the model. That's fair, great. But think of a case where you have 5% donors and 95% non-donors. Maybe a smart strategy to do in terms of technically predicting it right, maybe to predict everybody as non-donors. That's easy. Then you have 5% error rate and 95% accuracy rate, right? If you predict everybody to be non-donors, you are correct 95% time. But does it solve the problem? It's not realistic. It's a smart strategy to boost the performance, but it doesn't solve the problem. right? So instead of prioritizing the prediction accuracy, you can prioritize the expected profit based on the decisions that the business do according to the predictions. So here is the step that you do to intervene with that sort of the more conventional precision-oriented strategy to profit-oriented strategy. You attach different cost structure to different decisions, so that the algorithm is will try to maximize the profit by making predictions. So then you get better return instead of simply being right. So let's take a closer look at the decision profit here. Let's say there are only two outcomes here, right? A person is either a donor or a non-donor, and the result will be that if the person is donor and you happen to send a solicit to the person, then you will get a big return, right? But if the person is non-donor, even if you send something, he or she is not going to donate. And whenever you send a solicitation by mail, let's say this is the conventional setting. This is mailing the solicit to the potential donors. So every mail is going to cost 50 cents. That makes sense. That's postage, right? And paper production cost. But every time you get a donation, you'll get a big fat check. So here we need to put in those numbers. What do we expect the business to lose or earn based on the outcome of the decisions of the donors? So here, let's change it, and I'll explain what does it say. Let's see. I think decision weights. That's the decision weights, and here is for you to customize the labels for different decisions. We'll keep it as default. So here, the level means the target B. So does target B equal to 1 or 0? It equals 1 when the person donates money, or equals 0 when the person doesn't donate. And decision 1 and 2 means decision 1 is when the business sends a solicit mail. Decision 2 is when the business ignore the potential donor and doesn't do anything. So hopefully these two decisions will be aligned with the outcome. You want to send as many solicit mails to those who you predict as high likelihood to donate, right? You want to ignore as many people who you don't believe they have a high likelihood of donations. Okay, so but sometimes you'll still make mistakes, right? You'll ignore those who actually is going to donate but you didn't recognize, and you're going to send some mails to those who actually not going to donate but end up to be a cost for the company. So here is the expected profit, is the gain minus cost of the decision and outcome. So under decision 1, if the outcome is 1, then you send a mail, you incur some cost of the postage, you get a big fat check. Let's say the check is expected to be $15, and minus the 50 cents is 14.5. So that's the expected return or profit of this decision under this condition. What's the other condition? You send a mail, but you didn't get a check. So that is going to be minus 0.5. Is you have some costs, and we actually going to revise it to 0 under decision 2, because under decision 2 the company is not losing anything and not gaining anything. So it's the non-action choice, right? So this is going to shift the weights of the algorithm so that it will prioritize the accuracy of predicting donors and the accuracy of not predicting non-donors. But instead of simply being, treating them as the same, right? Giving them different weights, we'll treat them differently. So now we can do okay. Question,
Professor,
Kevin?
If there was that lost opportunity where the company didn't act, that person
Yeah.
would have actually donated,
Yeah.
would we have assigned that like -15, the company lost out on that potential, or we don't think of it that way? It's just 0 no matter what.
That makes sense.
Well, I don't know.
Yeah. So, the way you assign weights, it does have some requirements. It doesn't consider opportunity cost. So what you're just described as opportunity cost. If you don't act on somebody who is going to, donate, it's opportunity cost of those dollars, right? Okay. So from that window there, from those numbers to the actual reality, there is some little gap in conceptualization. The table actually does consider that situation is when you say, your return is 0 under the decision rule if the person is actually 1. But your return is 14.5 when your decision is 1 for those people, right? So on the algorithm level, the algorithm will get feedback whenever it makes a mistake of tagging the donor to be non-donor, and in that case, the algorithm in the training process it will recognize the opportunity cost and try to optimize that weights to minimize that mistake. So yeah, there is a distance there from the categorization to the actual process, but I assure you that is happening. Because the trick to specifying the weights is not thinking about opportunity cost, but thinking about real costs. Very good question. So we basically we finished the first sample project, and in fact the decision criteria and weights and stuff like that, we're going to hit that maybe in week 8. That's quite advanced stage of making predictive models. First, we try to make a model that predicts with the lowest accuracy and treating different outcomes to be equally, having the equal weights. And based on that, we will evaluate different models, but the evaluation is going to be contingent on the specific business cases. And that's when we introduce the decision weights and decision criteria. Any questions other than what we had? Good? So, I think let's, why don't we keep doing the several mini tasks here. On chapter 4, we have a replacement task. Let's see. Oh, we do have to do these. Okay. Yes. Okay. So we need to create a diagram. Donation. And the first node is always going to be the data source. So what you do is simply to drag from the list of data source to the area. But keep in mind that this creates a copy of the data set. So then from this point on, whatever you do here is not going to be reflected on the node in diagram. So you would have to change over there. So this creates a copy. In chapter 4, we'll introduce some analytical tools. So I'll quickly demo that. And the first thing is what you typically would do in any project is to use a tool to summarize the variables inside this sample. So under Explore, we have a Stats Explorer that looks like a bunch of symbols. It will click and drag onto the diagram and make a link. Questions? No? A couple of things to change before we run it. And notice that there isn't a green marker there, right? We haven't run it yet. When you, after you highlight the node, after you highlight the Stat Explorer, its property panel will be activated. And we need to change, we want to know about the interval variables as well as the class variables. So we need to change this that's under train, big heading, and under the small heading is the chi-square statistics. Modify for the interval variable also to be yes. And in a minute you'll see the difference, or you'll see the effect. And that's the only thing we change. After that, you will right-click and run it. Or I guess the other way is to highlight that, whatever the node that you want to run, and click the shortcut. And running any node will activate the running process for any of the node preceding in the upper stream of the sequence. Right? So it will, SAS will check whether or not any of the upper stream nodes have run. If not, it will run it. And until it finishes the last node. Okay, click results. Oh, you get 3 windows. So the information here, this window tells you the overall relationship between each of the input to the target. So basically what it does, it ran a simple decision tree model in the back. So by doing this, you actually have run some decision tree models, but very simple ones. And the SAS process does it all for you in the back end, and it does it for every of the input variables here, so one at a time. So it has run a bunch of models in the back, and it ranks by a statistic here. This statistic basically quantifies the association, or the sort of the extent of informativeness of each of the input variable in helping you predict the donor. Does that make sense? So the variable worth of each of the input variable. You know, by simply using one of these variables, how much gain do you have in improving your predictions? So that's simply put, right? It's a direct comparison of the relative usefulness of the variables. Question?
Yes, Professor. Does each of those, that all adds up to 100%? That's what that's the takeaway? It is, if you added up all those bars, would it equal 100%? No?
It doesn't. No. It, let's see. That's a good question though. So the variable worth only considers a pair of variables. So similar to correlations, if you can imagine. Correlation is the amount of covariance between two variables. So right, so you can have a correlation matrix of many variables, but you can't simply add the correlation together. they would not make sense. So these are pairwise statistics, and those are not addable, if that makes sense. But this gives you a straightforward overview of what might be some of the variables that are likely to be informative and you want to include in the final model. So I want to take a guess of which variable might be the most informative about making predictions for a donor.
Socioeconomic sense.
That's a good one. Like education, those kind of information. What else?
If they are previously donated.
Yeah. That is actually a closer. So some of these variables might be very close in terms of the stuff that it measures to the target. The target is whether or not this person donated this time. But then, an intuitive predictor would be whether or not this person has donated ever. So if a person has donated ever, it's much higher likelihood that this person is going to donate sometime, in the future. So it serves as a good, even sometimes better than socioeconomic status. The first one here is the frequency of the donations. So it is cumulative information about this person's habit of donation, if you will, something like that. So it does have information in there. And on this output window, it provides specific information about about an overview, or it's not individually, but an overview of the common statistics of these variables. One thing I would like you to notice is the number of missing values of each of the variables. It breaks it down to two types of variables. One is interval, the other is the nominal type, which is another name for a nominal variable is class variable. Categorical variable, class variable, or nominal. So all of these are nominal variables, including the target. It's binary, and there is no missing values here. So for the 20,000 record, 20,000 observations, we have full information in this, in these variables. But if you look at the interval variables, we have a longer list. There are several variables for which we have thousands of missing values. But one thing that we would definitely expect to have a large number of missing values is target D.
Yeah.
We won't observe for a large part because they didn't donate. Yeah, but target D is rejected, so we won't find it here. Okay, and it also shows some conditional correlations between the target and some of the input, depending on the case, depending on the outcome. So there are a wealth of information here. Okay. And the chi-square is quite similar to the variable worth. It's two different statistics that try to measure the same concept, but because the way of calculation, the formula is slightly different, so the ranking might be slightly different. But here, the number one variable that predicts the target is the same under two different metrics. It's the frequency status. So there are quite a large amount of similarities in the rankings. Okay, so this gives you a quick information about the big picture. Question?
I have a question.
Yeah.
Yeah. The worth on the side, its units, is it probability with different units?
No, it's a worth statistic. And so
Limited.
it's very small now, but it doesn't mean it's meaningless. It's very small. It could be because the distribution is quite, complex.
And what's the
Yeah.
maximum, like, that's
That's interesting.
more thousands out of what?
For
Like,
thousand,
Yeah,
like point, like
yeah, like
3 decimal
thousands
point.
out of what?
Yeah.
Like,
Maximum, I think 1. Yeah. I'm not even exactly clear because it relates to the technical details of the models. Let's see. So yeah, that's basically what we do. For a tutorial, we're gonna create a partition of the entire sample. The point is to have a mechanism of cross-validation. Right? If you know the concept, if you know about overfitting, that's great. But we're going to learn it in a couple of weeks. That's a cricket. So we'll finish the partition and we'll take a short break. Partition is it's not under Explore tab. We'll have to say Sample, I think, under Sample. Data partition, you will drag behind that and connect that. There are some numbers to specify for this partition. So basically, we need to have a training set and a validation set. So we allocate 40, 60, 60, 40, 50, 50. The exact choices of which is a little sort of it's a judgment call a lot of times. For simplicity, we'll keep it 50-50 for now, and we'll keep 0 for test. So yeah, so in the future, in model results and where we evaluate the models, we'll refer to train and validate. So when we say train, it's a training set. When we say validate, it's a validation set. We run it and we take a look at the overall statistics. So basic idea of, or to make sure that the partition does its job, we want to make sure that the two partitions are randomly made to the point that there's no mechanistic differences between the two partitions. We want them to look very similar on the overall distribution of the variables, to the point that each random partition can be seen as a typical random partition of the underlying sample. Does that make sense? And we want them to be similar because we'll have the algorithm learn from one partition and try to predict the other. So you would hope that the information contained in two partitions are similar. Otherwise, it's going to be problematic, right? So after the partition, it will give you a very brief report. It will give you the percentage of the different values of the target in the original sample. So for target B, we have two values. Possibilities, we have the percentage 75 versus 25, 75 being 0. And under the two partitions, we can see that the number of zeros are very close to 75%, if not exactly the same. It couldn't be exactly the same. But as long as they are very similar, they're almost unnoticeable, then it's good. It's good.
So if they're not similar, do we go back and change our?
You can change the random seed
Okay.
to try. So by default, SAS will use one random seed, which is 0, I guess. You can change it to a different random seed. It will generate different random samples, right? But if you keep doing random partition using the same seed, you will get the exact same samples. If you know the computing, background. It's rare case, the larger data set that you have, the more likely you'll get a similar partition. The smaller the data set you have, it's going to create unique data sets under some conditions. So you won't watch that if the data set is small. Right? Okay, let's take a break. We'll come back at 7:50. I'm pausing the video here. Okay, resuming the recording here. All right, so I'm gonna demonstrate one more task here, is to replace some of the values here. Just a heads up, there are several nodes that does things that are kind of similar and confusing. For instance, this one that I'm going to demo is replacement, and there's another node which is imputation, impute missing values, which is also replacing missing values. So both of them are replacing, but by different mechanisms. There's another node which is in chapter 5 here, is transformation, which is also making some changes to the data set, but in a different means. So for the high level difference here, replacement is more of a hard coding, is you specifically replace a value of a variable with another specific value. So that's sort of a hard coding problem, right? You're changing manually, but instead of changing individually, you're using program to change it in bulk. But the mechanism is the same. Now, imputation of missing value is by using algorithms to figure out what might be the most likely value if the value was not missing. So that is using algorithmic mechanisms to replace. So you don't even know what the algorithm will replace in that specific case, but you have some confidence there because it is running a machine learning model in the back to try to figure out what might be the best way to replace the missing value. So that is more of a algorithmic based replacement rather than hard coding, right? And transformation is not exactly replacement, but sounds like so. Transformation is making a systematic change to the scales of a variable. So like taking the logarithm of a variable will modify the distribution of that variable, if you know a little bit about the background. Now, the tutorial explains something about logarithm transformation and what it does, but when I talk about the slides, I will show you what is it for and how do we do it. These are the technical means of doing that. All right, so we'll do a replacement here. Replacement is under modify. So do the drag. So here we're changing two specific levels of two nominal variables. So we're specifically targeting a level of a nominal variable and to replace it with something that is more appropriate. Under the train, you have the replacement editor. I believe that's a place. Yeah. Under class variable, not under interval variable. So it's here. Can you see it well on the screen? The fonts are good enough? Great. So under the class variable replacement editor, you will see a list of class variables, nominal variables. and the entire list of unique values under each of the nominal variable. So the cluster code has a lot of values. It's the geographic clusters code. So every cluster has a unique value here. So that's why there's many. We are going to change which variable? SES is the socioeconomic status. So there's a slight problem here. The data set is likely obtained from an old system, probably a system that doesn't have an internal means of representing missing values. So for any missing values, they will use a question mark. But question mark to SAS doesn't mean missing. It means a unique category. But we want it to denote as missing. So we will replace it with underscore missing underscore. That's the way we will code it. And same thing with urbanicity, has another question mark. We'll do the same. So after that, you can go ahead and OK. But don't forget to run. Basically, take a look at the results. It reports what have been done and allow you to take a look at the data set. I think there's something I skipped, and why? Because I see all of the replacement variables made to almost the entire data set. But there's a way to fix it. Under interval, with the replacement, under train interval, something that I have forgot to do is to change it to none. So what it does by default was the standard deviation from the mean, and the cutoff value by default is probably 3. So what it does is it looks for any extreme values that are lying 3 standard deviations away from the mean, and will replace them with missing. And this way, in some situations you prefer to do that because you don't want those extreme values to bias your model. But for demonstration purposes, we don't want to do it here because it's making too many changes. So changing that to no will nullify the action. So it will not do that. Okay, with that change to no, and with the replacement editor already changed, we'll run that again. Let's see. Did that happen again? So the replacement of the class variables that did take place from question mark to blank, which is missing. Let's see. Did this happen? So yeah, so I failed to change it before I run it, so I changed it back. to explain it. So I have to do it again. So it's always a good idea to check after you have done something to make sure, it's a back and forth process, but making sure that you have done what you want to do. And I'm going to demonstrate another way to check the actions. So here, simply the two variables that are changed. And here, this table shows you the number of values that are affected by the replacement. So only 231 observations gets changed under the training. Remember that we have two partitions right now. We have a train, we have validation. So the numbers are slightly different. Okay. Now, each of these nodes save a copy of the data set after it does something, right? And you have the option to get the data set out, to output the data set, to look at it if you want. Do some diagnostic checks and use others, use the SAS-based software to do any statistical analysis if you want. So what you can do is you highlight the node after you have run it, and you go to Exported Dataset, and click that. You'll get a list of possible data sets, but here there are only two because we didn't do the test. We didn't do the other tasks. We have train and validation. And for these, you can browse it, or you can save it even. You can do exploratory analysis, which I will cover in the next 2 weeks. You can browse the training data set after the replacement, and you can see the changes. So the two new variables that are created after the replacement has the replacement information in the label, and a lot of it here is are missing, but that's true for the original variable. It does have thousands of missing values, and by default you won't be able to find the original SES variable because it's automatically rejected from this point on. It doesn't make sense to keep both in it because a large part of the information will be the same. So you want to only keep these two, but not the original two variables. But even though it's rejected, it's in the back end. It's in the project file somewhere. You can still get them if you want. But for the process sake, for the further steps, after this step, you won't need to use the original two variables because the values are replaced. It's a better version of the variable, if you will. So this is another way to check that you have done what you expect to do, and by looking at the output to find sort of the indicators of the correct operations. All right, so I'll skip the chapter 5, and so you can do that as a take-home homework. But do let me know if you have questions. Previously, I was demonstrating the first project. I think I did until after I have finished data partition. Did I do anything after data partition? Can anybody remind me?
The chi-squares,
Chi-square.
the graph.
Yeah, that's I believe that's in Stat Explore. Yeah, I think so. And after Stat Explore, I did some is that cherry replacement. I replaced some values of a couple variables with missing. I think that's Yeah, that's the deal. And there are two tasks or two techniques that are in the tutorial, but I didn't demo, right? Can you remind me what are those? If you have already gone through them, that would be perfect. Then you know what I'm talking about. I think that's the sixth chapter of that. Do you have it? Do you have the tutorial?
You said that over it's chapter 6.
Yeah. Did anybody get a chance to go to follow the tutorial and did it yourself? Yeah, Senanshu, what are those topics? I remember one is transform variables. What's the other? Regression? I think regression is the other chapter. But the same chapter with the transform variables. What is the third section? Replacement? Well, the binning. Oh, that might be it. The binning. Yeah. Right. Ah, so binning and what's the other? Log transformation. Both of them are in transform variables. Yeah. It's coming to me. Great. So the point of I want to mention homework 1. Yeah, homework 1 has some hands-on problems, right? It asks you to do 3 things. One is to find the missing, to report the extent of missing values. What tool would you use? What node would you use to do that problem? Stat Explore. Exactly. Yeah. Stat Explore. It's the second node that we did here. In the results window, it will give you an overview of the number of missing values in each of the variables. And the variables being separated into 2 types. One is class variable, the other is interval variables. Great. The second question was asking you whether or not you can find any problem with area codes and states. Right. In terms of identifying or discovering variables that are abnormal or values that are abnormal, the best tool that you have or best mentality that you have is using visualization tools, using exploratory and graphing techniques. But there are different tools available and appropriate for different kinds of variables, right? If you remember, let me see. Let me bring up the slides. Control. So tools like this, histogram, would be best for trying to discover if there's any outliers in interval type of variable. You can simply make a histogram and then see if there are any bars that are lying away from the group of values, and you can quickly identify. Using scatter plot can even find relationships between abnormal values across 2 different variables. But that same technique, at least it can help you identify abnormal values the same way, or will reach the same conclusion as if you were using the histogram, right? But this view will give you 2 dimensions of the data. So things like that. But these are interval variables. What about categorical variables? what kind of graph do you have available to you? Right? Can you think of any?
Pie graph.
Pie graph, definitely, yeah. Pie graph will show you the proportion of observations in each category, and and you can rank the categories arbitrarily or according to some kind of alphabetic order, right? Definitely. There are other tools similar to pie chart, but give you a different flavor or a different perspective of the data. It's a bar chart, basically. Bar chart, lie them horizontally or vertically. The idea is the same. You can get a sort of the big picture of how much each level is represented. So, in order to identify if there's any problem with the area codes and state variable, both of them are class variables, you would make graphs, either kinds or both, either by pie chart or bar chart or both, and look at each value specifically. And the kind of problem you may discover will be something like that we kind of touched on previously. I think it's missing. Here it's a table, but imagine that you make a bar chart or pie chart about the different brand countries, the origin of the automobile manufacturer. If you imagine a pie chart, and you have a piece with USA, you have a piece with France, you have a piece with US, and a piece with Europe and possibly others. And the piece about USA and France will be tiny. The piece with the others will be major, bigger pieces. And so you can immediately, kind of sense some concern. There's some data in the data set that is very, less represented. And when you look at the label and all the labels and you examine them, then you start to see overlaps. But for categorical variable, by design, it should be mutually exclusive labels. So that's the way you would look for possible errors. That's one scenario. But also, imagine that you're doing a pie chart with the U.S. states. And let's say, and you found 13 states, as if there are 13 pieces of the pie in the graph. What would you think? And what would you do? I would look at the 13 labels to see if there are states of the U.S. as the data set was supposed to represent, and I'll think about if 13 states is a good number here. Should there be 50 states? Should there be fewer than 13 states, or why 13? That's my question, right? So that is another approach, but using the same technique. So I would suggest you use the same technique to approach that question. And it's something else I'm going to talk about a little bit later when I demonstrate SAS that is kind of related to this question as well. The third question is asking you to transform. Yeah, great. So that will bring us to here. So I'm going to do a transform variable demonstration here following the replacement. It should be in the modify somewhere here. transform variables. Okay, so is that mine? No? Wait. So in the tutorial, transform variable node was used for two purposes. One is to log transform some of the variables. Another utility is to, what did it do? Binning, the binning part. Binning is slightly more complex. I'm going to talk about, hopefully, if I had a chance, I would talk about later. For log transformation, the purpose is basically to make the distribution of a variable more normalized, right? It's to increase the normality of the variable by not fundamentally changing the information that's represented by the variable. And why do we need more normal distribution? Because some of the models, including regression, its performance depends on how far away the distribution is from normal. If it's highly normal, the performance is expected to be optimal for regression. If the distribution is highly skewed, highly different from normal, there may be some problems with the predictions. Okay, so let me go specifically into transform. There is a when I highlight the transform variable, there's a tool very neat. Go to the formula. You can construct a custom formula to specifically transform these variables or selected variables in a way that you want, like +1, +2, +3. You can construct a formula. But the reason I'm using this is not for customizing the formula for now. The reason I'm using transform variable, I'm using the formula tool here, is to quickly get a sense of the distribution of the variables without generating different graphs. So here you'll get a list of all the variables, all the input variables here in the data set. When you scroll through the different input variables, the either a histogram or a bar chart is created for you at the upper portion, and it's so quick that it's almost instant reaction. So and when I want to examine the distribution of the variables, this is the quickest tool I can go, the most efficient place of the software I can go for a quick visual examination of the different variables. So let's look at some of the variables. I would suspect that the donor age variable to be fairly normally distributed. It's okay. It's not very normal, but it's not very skewed as well. It does have a heavy representation by senior people here, people aged above 60. It's a large proportion of senior people. But then if I link that to the purpose of the project, then I would probably understand. Because more senior people tend to have more money to donate because they don't have kids to raise, and they tend to be more generous, hopefully. So it works somewhat favorably to the project. But if I look at another variable, lifetime gift count, how do you think that the distribution will be? Is it going to be close to normal? Is it going to be symmetric? If it's skewed, in which direction do you think it will be skewed? Where's the tail? Left skew?
Left skew.
So the tail will be extending toward left. So those who have fewer count of gifts will have less representation in the data set. And then those with the higher, larger value for gift count will have higher representation in the data set. Does that make sense? So that means the bars for larger values will be higher. The bars for fewer values, for smaller values, will be lower. That's left skew. Does that make sense? You have more people who are donating a lot of times. You have less people donating a few times. Does that make sense?
Well, we used to compare the mean and the median to decide which way that.
That's right. That technically, yes.
Then
Technically, that's how skewness is defined. You compare the mean and median. But visually, you can get a quick sense. It's where the tail is pointing to. So let's take a look. Gift count. Is the tail pointing left? It's pointing right. So that's somewhat, it's opposite from the story that was narrated earlier. It's those who donate a lot have a lower bar. It's those who donate very few times or even none have higher bars. The bars represent the percentage of the data set. The bar is representing the frequency, right, of that value. So things like that, it's understandably right skewed because fewer people would be willing and able to donate. More people would be, willing to donate fewer or try to avoid donating if desirable, right? So this is a typical case of a right skew. You can think of many, many scenarios where a variable is right skewed. Income, right? Wealth, income, the same thing. I don't know. What else? Number of children. Definitely, yeah, definitely. Yeah. Although you can also expect a small tail on the left, but the right tail will be much longer. Just because there is a cutoff here, it's not going to be possible to give birth to -1 children. It's only possible to give birth to 0 and none, 0 fertility. But it's still possible to give birth to 20 kids in a lifetime, right? But those would be rare cases. So that's why it's right skewed. Here, it seems that the vast majority of people has given 1 time because the bar is highest, close to 1. That may give you that impression. Question?
what does your x-axis represent?
The gift amount,
The
gift count,
donate
number of times that the person have given.
throughout the whole lifetime.
Yeah,
Okay.
yeah, or as much as the data can collect.
Okay.
Yeah.
So more people will donate in that specific area.
Yeah. So the larger percentage of people have donated between 1 and 9.8 times overall. So this might have given you the impression that the majority of the people in the data set has given 1 time or once, right? Does it?
It shouldn't, because it's not showing how many people haven't donated or never donated. Maybe.
That's right. Yeah. It seems everybody has donated at least once in this data set, which also makes sense. If the company only targets those who have donated, then it may make sense to them in terms of increasing the chance of getting donations. So, but we can we can extend beyond the scope of these exercises to talk about those. But I would defer talking about those for now. But the point is that you can get a quick glance of the distributions by using this tool very fast. And later on, I'll demonstrate another alternative to generate these same kind of graph, but it'll be much more time consuming. Although it gives you more control, it's more time consuming. Okay, so while we stay in the transform variable node, we will do some specific transformation here. Under training for variables, let's go into it. And while the tutorial talked about log transformation is to fix the distributions. So for variables like gift amount count, or everything related to average gift, everything related to the gifting histories, you would necessarily find the distribution to be skewed. So you want to take a log transformation on these variables, as the PDF tutorial have demonstrated. The quickest way is to select everything that you want to apply the same kind of transformation, and then you just click one of these for the method and choose the right method that you want to apply, and then it will apply to everything that's selected, right? So, but however, if you want to apply another transformation, such as such as this, then you will do the same thing here, and then select whatever method you want to apply for transformation, and then confirm. Confirm by OK, and then make sure you run the node. Yeah. After it's successful, it's always good practice to check it, to make sure nothing, unintended has been done, and everything has been done as the way it's intended to. For these results, it gives you a summary of what has been done here. So for these variables, they are treated as input, as the original values, and some operation has been applied to them, like log transformation. So the new variables are computed and included in the output data set that's coming out of that node, right? It has a new name. It has a prefix of the type of operation that you have applied. For instance, these log indicates that I have applied log transformation to these variables. SD or STD means I have applied standardization to this variable. And same thing here. It just gives you textual feedback. But it would be nicer to generate some distribution plots to make sure that if it's a log transformation, then the distribution has become more normal, to compare what was before and what was after the transformation, to sort of give a visual demonstration that you have done it and it's correct. So in that sense, I will then use the exploratory graph tool. I could also drag another transform variable here to connect to that and to generate those graphs for those that have been transformed. Does that make sense? Right? But doing that twice it's kind of, I don't know, you can do that definitely for the homework, but it's going to be the same technique. I'm not going to demonstrate it, to save some time. I'll use an alternative here. So this is a process model of data mining. And imagine that there is a data set that is being passed through this stream. And there's a data set accepted as input and and feed into the first node for analysis. And something was done probably and applied to the data set, and it's passed through to the next node. So this kind of a morphing data set is passed through. And by the end of it, you have an output data set that is, that has changed because of all the operations that you have done. How to get those data set? After highlight the node, you can go to exported data. That is where you can extract the exporting data set. And you can do some exploration on these. So this is what I'm going to do. The mission here is I want to generate some distribution graph about those variables that have been transformed. One is log transformation, the other is standardization. By looking at their distribution after transformation, I should see a difference, right? So in the exported data set, I have two data sets. As you can imagine, I have already done data partition. So all the transformation have been done, applied to both of the sets. I can choose one of these. After highlighting that, I can do explore. And so this explore tool is ubiquitous. You can find it everywhere here in SAS EM. I just haven't pointed it out to you yet. This is one place you can do it. But keep in mind, try to remember, every time you use explore, try to remember to change some setting here. Unless your data set is immense, like 100 million, that would be immense. 100 million records, that's immense. That takes a lot of memory, and takes some time even for SAS to process, and that won't be worth it. And since the data set is large, you can take a random sample of that big data set to do exploration. But here, for this course, most of our data set is not immense. So make sure you get the full data set to explore rather than a sample, right? So something to remember is whenever you're going to explore, you make sure you change the default to max. Default is saying it's taking a sample. It's taken a small sample of the entire data set. But using max is trying to use the entire data set and apply. And that's done. So you can see that the fetch rows has become has changed from 2,000 to 9,000. Now you're using the full data set to do explorations, and that gives you the most accurate exploration results, right? Now you're ready to generate some graph. It's in actions plot. And then you have a whole range of tools here. You have different graphs to make. Let's quickly make something. So I want to look at the distribution of the continuous variable. So what graph should I use? Line graph. What is line graph? So line graph is more like scatter plot linked together by lines. You have two dimensions. You have x and y, right? Does it give you the distribution, or does it really give you the correlation between two variables? It's rather those bars. But for continuous variables, we call them, by convention, we call them histogram. They look like bar graph, but they're histogram because the bars are sorted. As with bar chart, the sorting can be arbitrary, right? But histogram has the bars sorted. So we want to use histogram. The default type is OK. We go to next. We choose the variable to do. Question?
How did you change the number in the fact
Oh, okay. The sample, right? So right after you go into explore, you would change default into max, and then you hit apply. This number will change. Yeah, great. And so actions plot again, histogram, next, and so choose the variable. Can you tell me which variable I did log transformation, and pick one. Lifetime count, and it will be obvious here because it has a log here, right? It has a log, and since previously I looked at gift count, so I look at the gift count. If you remember the x-axis previously, it's between 1 and 80, maybe something like that. Lifetime, change the row to be x, and for histogram, there's only one variable needed. And on the y-axis, you can choose to display frequency or percentage. You know, slightly different versions, but give you the same shape. I'll do the percentage for now. This one is modifying the name. It's not necessary. Or setting some conditions to filter the rows. And we don't want to do that. And give some customized title. Footage, none. X is log. Count. Gift. As long as it makes sense. Y is percentage. Or do percentage. And we can toggle X's on both sides. So that's it. This is the distribution of. So what do you notice? Is the distribution the same, similar, or very different? Do you see a long tail? The long tail is gone. Yeah. And what else?
The range is reduced.
The ranges have changes. The minimum now is 0.69. Yeah. And the maximum is 4.5. Something close. So it is a dramatic change, right? Can you imagine what the log transformation is doing? Kevin? Han?
It's normalizing the web.
It does. Yeah, it's eliminating the long tail in a large part, right? Kevin?
No, I was just gonna ask it, is initially usable because we can only have integers of how many times gifts were given, so
It's a good point. Yeah. So the values are now not making much sense for gift count. It makes a lot of sense. Yeah. So this change to the variable, it does have plus and minus signs. It does correct the distribution. Is everybody clear on, first of all, technically, is everybody clear on why it's correcting the skewness of the distribution? It's okay to say no, because then I will demonstrate. If everybody's clear, there's no need for me to demonstrate.
Please demonstrate.
Okay. Perfect. So, hopefully this works. It will help if if we review a little bit of a background of what does log transformation do. So, even if I use log instead of log 10, it's the same logic, right? Log 10 of 1 equal 0. Correct me if I'm wrong. Log 10 of 10 is 1. Right?
Yes.
Yeah. And log 10 is not defined. Right? Anything equals 0 or below 0 will be undefined. So this is the original variable, and this will be the log version of the variable, right? So what was a 1 becomes 0, but what was 100 becomes 2. So you can imagine that if the original variable has this kind of a distribution in terms of histogram, then if this is 100, then after log transformation it becomes 2, right? Very, very small, and this is 0. And what was 10 become 1, right? So after transformation, it will kind of become this. So that's why the tail is gone. It's the sparse regions are pushed toward those lower values, and then everything is squeezed into this distribution that looks more normal. Yeah. So that's why, technically. But the problem is it's making the values nonsense in terms of what the variable is supposed to capture, right? It's supposed to capture the total lifetime count of gift. So then the question really is it valid to do that? Like what problem might it create if we do that? Sorry, I can't record that. So when you hear the recording, this is gonna fade away just because I'm far away from the mic. But there's no other solution for now to that. This is one. This is what a log transformation is doing. So this x-axis, you can imagine it to be original variable, and the y is the log version of the variable. If it's 1, then after log transformation becomes 0. If it's 10, it becomes 1. So that's a correspondence. It does change the value of that, but it didn't change the comparison, evaluation of the relative, not relative, of the arbitrary comparison of two values. So if we have two values, this is out of scale, but pretending that this is 100, after log transformation becomes 2, these two values, 100 is bigger than 10. After log transformation, it's still bigger than 10, although it's not bigger by that much of a scale. I can't say for sure what is the term in mathematics. Can somebody remind me? But this is the, monotonic correspondence between the original and the converted variable. And it is fine to do that here because we can always convert back. So it makes the case that we can do that. Does that make sense? Kevin?
Professor, sorry, the default, we'll call it log function here, is it?
It's a natural log,
or is it
yes.
Natural log?
It's a natural log. Yeah.
So then is it just, I guess, is it just changing the bins or the classification? Because then I guess you can change that back, like I did e to the 0.69.
E to the, it's 0.1, 0.3 or something like that, 0.5?
Well, according to this calculator, e to the 0.69 is rounded up to 2. It's like 1.99. So I guess it's saying that.
It's 2. Okay,
counts
right.
start at 2, and they end at
That makes sense.
e to the 1 would be maybe like 3. So from 2 to 3.
Yeah, that makes sense.
10%, and then it. So I was just asking.
And we can can we generate that? Yeah, the original variable is rejected by now because it's being transformed. So the original variable is hiding from this node. So to directly compare them, it takes a little bit of time to prepare. But you're right. By conversion, the minimal value of that variable is 2. Yeah. 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 So for models like regression, it benefits from converting the highly skewed variables to become more symmetric. Okay. I need to bring that the other table here. There we go. Okay. Now, so this is for log transformation. Another thing I did is standardization, right? So for standardization, I skipped some of the slides last time. Or no, I didn't skip, I didn't get to it, essentially. So let's review it quickly. That's a binning. Transforming, no. Right. So this is about normality of distribution and how log transformation can correct the skewness. So these are about the theory side. Where is the standardization? 31. Thank you. Great. So, z-score standardization. Essentially, what it does is to convert any distribution into one that has mean 0 and standard deviation of 1. So in a way, it kind of squeeze and remold any distribution into someone that is somewhat comparable to each other. So every variable after standard deviation, z-score standardization has the same mean 0 and standard deviation of 1, so that you can see, in that scale how they are distributed specifically. It helps with neural networks a lot. It doesn't help much for most of the other variables. So regression doesn't need standardization, although the interpretation of the results may benefit from standardization, right? So for any distribution that may have a mean 10 or mean 100 and standard deviation of 8, after standardization it will have a mean 0. So it's kind of centered around 0, and the spread is kind of readjusted to have a standardized spread. So I did a standardization on age, right? Age has a spread of between 18 to 80 something. So after I standardize a variable, it should have a mean 0, roughly, and a spread, a range of between -4 to +4, something like that. So I should expect to see that when I do a graph. Right, so I'll do another graph, same histogram, but this time on the H variable with the standardized STD H. Oh, by the way, I do see the original variable here. I do see the donor age. So later on, I can do the distribution of the other. So for donor age, select X. I will use frequency this time, but you'll see the difference. Histogram of standardized age. Standardized age. Y-axis is the frequency. So this is the distribution of age after standardization. The shape of it didn't change. It still has a high bars and higher values of age, although the values are now not in the scale that we come to understand age. It's between -3.5 to +1.6. It may give you the impression that it's not symmetric. It is not symmetric, but because of the skewness there, you know, so the median here is not 0, but the mean is still 0. It's for sure. By definition, standardization will make the mean 0, and because of the skewness, the median is not necessarily 0, so it doesn't overlap with the mean. That means there are skewness. So by providing this graph, you can demonstrate that I have done standardization correctly on this variable, right? And the good thing is that we have the old variables. So I'll bring that up. I'll do this first. I'll do the histogram of the original variable for gift count. So y'all can do your own way, or you can follow me. Maybe you're faster than me, which will be fantastic. Lifetime gift count. Yep. So I'll do the same thing as percentage as before. And now I'll skip the other things, but I'll do the X. This is gift count original. If we compare side by side the two graphs, the one on the right is the original gift count. The one on the left is the logged gift count. It's a dramatic difference in terms of distributions, skewness particularly, as well as the range of it, right? But the two carry same information, not exactly the same, but after conversion it's the same, right? And something neat about SAS is that these graphs in the same view, in the same node view, is linked. So their IDs in the back end are linked together. If I choose a point in this graph, it's going to be highlighted in the other graphs automatically. And because I said the log transformation is monotonic conversion, right? So if I select those lower range of values here, which part of those bars do you think will be highlighted? Will be selected, highlighted, because they're linked. Same lower ranges, right? Maybe not all of them, because by doing the log transformation, some of these values are kind of diluted into the other bars. So this is what happens. That's what I'm saying. Every data point that's included in this bar, or this takes this percentage of this bar. But if I highlight the other bar, it's going to be highlighting multiple bars on the left side. But you can see the correspondence, right? These are the exact linkages between the points. But only happens in the same node. Okay, that's all I want to demonstrate for homework 1 as well as beyond. Any other questions before we move on? Good. Great. Okay. Now, these graphs are not saved. It's not even possible to save them. So once I close this window, it's gone. So just make sure you know that. That's it. Okay. So let me briefly talk about the business world, what's happening, and we'll take a break, and we'll come back after the break. We'll do the case. Okay. This data science, data analytics, data machine learning, artificial intelligence. How do you think about that? How do you think about the whole movement of machine learning? I just want to know about your perspective. That's it. So I realize that people have different views, even on the same subject, even if probably have the same exposure to different information, but people have different views. I just want people to share these views. So feel free to talk and let me know. Let other people know. Kevin?
I mean, this is one thing that maybe I've heard. I don't know how true it is, how it isn't true. I don't know if there's a tendency to pick the lowest hanging fruits and say, all right, well, machine learning, has been